Our next topic of discussion is your stress tensor. Now, we know that stress is calculated at a point, right? So if you see that, suppose this is a member, this is a bar, and it is under some triaxial loading. On all the axes, that is x, y and z, some loads are there. Maybe it may be shear load or it may be normal load. So because of that load, because of that triaxial loading, this member is in stress, right? And we want to calculate what is the maximum stress induced in that member, right? Or what is the different types of stresses induced in that member. So to design this member, if you say the application of strength of material is machine design, to design this member, what I want to know is what is the critical section in this member. Means what is that section where the maximum stress is acting, and within this section what is the critical point at which maximum stress is acting. Because stress would be maximum at a point, right? Because stress is calculated at a point. So I can say that in this member, suppose this section is the critical cross section, and in this critical cross section, suppose this top point is the critical point. Means the stress at this top point is maximum, so this body will try to fail at this point first. So we want to know what is the different type of stresses acting on this point. So this can be known with the help of two methods. That what is the maximum stress acting at this. This can be known with the help of two methods, or we can represent the state of stress at this point by the two method. One is your graphical method, or you can say the stress tensor is the one method, that is a matrix form, and another one is with the help of Mohr circle, that is a graphical method, right? We will study the Mohr circle later on. So to define the state of a stress at a point, there are two ways. One is this matrix form, that is the stress tensor, and another one is the Mohr circle, that is the graphical form. So let us discuss what is the stress tensor is. The stress tensor is used to define the state of a stress at a point. We know stress can be calculated at a point only, that is the stresses acting on three mutually perpendicular planes passing through that point. Means that if you want to find what is the state of stress at this point, so the state of stress means what is the type of stresses acting on the three planes passing through that point, and these three planes are mutually perpendicular to each other. So one is this plane, your front plane, one is this top plane, and one is this side plane. These three planes are mutually perpendicular to each other. So we have to calculate what is the state of stress at this point. So if at this point, this is the point, if I enlarge this point, I will get this figure. This is the figure of this point, right? This is not a member, this is not this member, this is the figure at this point, right? If you enlarge this, now I can say that, let us say this is the figure of this point, that is a cubic figure or 3D figure. I am supposing let this is your x-axis, this vertical axis is your y-axis, and the third axis, this is your z-axis, right? I am assuming this x, y and z-axis. We know if this is the x-axis, so this is your x face. This is y-axis, so this is your y face. We already know that, we already studied this. And if this is the z-axis, so this front this front plane is, this plane is your Z face. There are three faces which are present, X, Y and this Z face. Now if I say that these faces are under the triaxial loading, so the stresses induced in these three faces are total 9 stresses. We already see, out of that 3 are normal, sigma X, sigma Y and sigma Z, and 6 are the shear stresses, that is tau XY, tau YX, tau XZ, tau ZX, tau YZ and tau ZY. We know this. And what is the meaning of tau ZX is on Z face in X direction? We already know all this thing. So if I represent the state of stress at this point, I am saying, let us say at this plane or on the X phase, the normal stress is your sigma X. On Y phase, normal stress is your sigma Y. And on Z phase, your normal stress is your sigma Z. Let us say this is your sigma Z. These are the normal stresses on these three faces, sigma X, sigma Y, sigma Z. Right? We are saying that all the 9 stresses are present. So on X phase, there must be a shear stress, that is tau X Y, that is the shear stress on X phase in Y direction. If I am saying, let us say this is tau X Y on X phase in Y direction, and there is this one that is tau on X phase in Z direction, tau XZ. Now on sigma Y or on Y phase, there must be one tau YX, right? Tau YX means on Y phase in X direction, and there must be tau YZ in Y phase in Z direction. And we already see that there are complementary shear stresses. That means that tau XY and tau YX, they are complementary shear stresses. Tau XZ and tau ZX, they are complementary shear stress, and tau YZ and tau ZY, they are also complementary stresses. These are the complementary stresses, and we already see that, and we will derive it later also, that these shear stresses are equal in magnitude. These complementary shear stresses are equal in magnitude but opposite in direction. All these three complementary shear stresses are equal in magnitude but opposite in direction. Opposite in direction means that if one shear stress will give you a clockwise movement, then another shear stress will give you a anti-clockwise movement to maintain the equilibrium. Right? To maintain the equilibrium of this member, I can say that if tau XY will give me a clockwise movement, then tau YX must give me a anti-clockwise movement. Now we have to represent the stresses like this only. This is tau XY, right? And this tau XY is in this upward direction, so this will give you a, because here also this is also X phase, here also there is one sigma X, there is also one sigma X, right? This is tau XY in upward direction, so there must be a tau XY in downward direction, right? Tau XY, and here tau XZ is in this direction, so tau XZ in this plane will be in this direction. This is tau XZ and this is tau XY, right? So these tau XY will give you a couple or movement in anti-clockwise sense. This will give you a movement in anti-clockwise sense. So the tau yx which is present in this phase and in this bottom phase will have to give you a clockwise movement, right? It must be giving you a clockwise movement so that this bar or this member will be in equilibrium. So if this tau xy is giving you a clockwise, then tau yx will be giving you this is anti-clockwise, so tau yx will be giving you a clockwise movement. So the direction of tau yx will be like this, tau yx, right? Then only this system will be in equilibrium. Now there must be one tau yz. So suppose I am taking this direction as tau. This is your tau yz. It may be anything because we don't know the tau xz or tau zy. So here we have sigma z. Here we have one tau xz. So if you see that this is the tau xz in this direction, here the tau xz is in this direction, this tau xz is in this direction, and it will be in this direction. So it will rotate like this. It will rotate like this, and if you see from the top, this rotation is clockwise. If you see it from top, and if you see it from bottom, it is anti-clockwise. You can see it from any one of them. So this is tau xz in your forward direction, tau xz is in this plane is in this inward direction. So this will give you a moment in this plane in this sense, and from the top this sense is a clockwise sense. So the tau zx which is in this plane, tau zx will give you a anti-clockwise movement. So I can write here that as one is tau zx. So if I can say this is the tau zx. Tau zx, this is in this direction and one will be in this direction. So it will give you a, from the top if you can see, it will give you a anti-clockwise sense. This tau zx is in this direction. The nib will show the direction. Tau zx, tau zx on your back of the plane. There is one plane in back also. So that tau zx will be in this direction. This tau zx will be in this direction. It will give you a rotation like this, and this rotation is your anti-clockwise. So the system will be in equilibrium. And there must be one tau zy. So you can say that this is tau yz in forward direction, this is tau yz, tau zy, tau yz on this top plane will be in your forward direction, tau yz on this bottom plane will be in your inward direction. So this is the direction. So it will give you a moment like this, and if you see from this side, this moment is a clockwise. This moment is a clockwise. So the tau zy will give you a anti-clockwise moment. So I can say that this is the tau zy. This is in upward direction, and this this tau yz is in this direction, this is in this direction. It will give you a clockwise movement. So if this is a clockwise, then tau zy will give you a anti-clockwise movement. So if you can say tau zy in this front plane is upward and tau zy on this back plane is downward, it will give you a rotation like this. This is upward, this is downward. It will give you a rotation like this. So if from this side you can say that this rotation is counterclockwise. So the system will be in equilibrium. Right. So these are the 9 stresses on these 3 perpendicular planes. Right. So if I show the matrix form of this will be like this, that the stress on 3D plane or 3D object will be like, you can write it like this. This is sigma x, tau xy, tau xz. This is tau yx, sigma y, tau yz, tau zx, tau zy, and sigma z. This is the stress tensor if you see that this is the stress on X phase, these are the stresses on Y phase, and these are the stresses on Z phase. These are the stresses on Z phase, right? Each row is giving you a stresses on your one phase. Now if I can say that the complementary stresses are equal, that means the magnitude of tau xy and tau yx are equal, magnitude of tau xz and tau zx are equal, magnitude of tau yz and tau zy is equal. So you can rewrite this stress tensor like this. It is sigma x, tau xy, tau xz. This is tau yx, which will be equal to tau xy. This is sigma y. This is tau y z on y phase in z direction. This is tau zx, which is equal to xz. This is tau zy, which is equal to tau yz. This is sigma z. So this is the stress tensor, and you can say that if this is a matrix and this is the principal diagonal of this matrix, this is the, you can say this is your principal diagonal of matrix or major diagonal of matrix. So the principal diagonal of matrix is a normal stress. On the other side it is shear stress, and this is this column, if you can say that this column, these three stresses are the mirror image of this. This is the mirror image of this. So you can say that the stress tensor matrix is a symmetric matrix about its principal diagonal. Is a symmetric matrix about a principal diagonal, right? These three values will be equal to these three values. So it is symmetric about this axis, about this plane. So this is the way you can show the state of a stress at a point. So if we can say, if in any question, the question will be like this. If in exam the stresses are given like this in a matrix form, it is given as, suppose this is 5, 1, 2, this is 1, 4, 0, like this it is given. So, and this will be 2, 0, 3, right? 2, 0, 3. If this, like this stresses are given to you, and we have to calculate what is the shear stress. Question will be shear stress acting along xz plane and in z direction, right? You have to calculate what is the shear stress on xz plane on z direction, right? What is this? xz plane means y phase. So we have to calculate tau yz. This is phase, this is direction. So tau yz will be 0. So this is 0. Shear stress will be 0. And if we have to calculate what is your shear stress acting along, shear stress acting along yz direction, yz phase in z direction, right? You have to calculate, or yz phase in y direction. If you want to calculate the shear stress on yz phase or in y direction, yz phase means, yz plane, this is yz plane. So yz plane means this is x phase. So you have to calculate tau xy. Tau xy. X is the phase, y is the direction. So tau xy will be this. This will be equal to 1. This will be equal to 1. So this is the way you can calculate, you can solve this type of questions. This is your gate question. So you can solve the questions like this. and this is the way you can represent the state of a stress at any point in triaxial loading. This is in case of triaxial loading, means in all the directions, in all the three perpendicular axes, the loads are there, so stresses will be developed in all the three planes. So this is the axial, or this is the stress tensor in three dimensional or your triaxial loading.